Good morning, guys. Today I want to wrap up our discussion on least squares regression lines. And we're going to do that today. We're talking about what we call coefficient of determination and actually calculating the least squares regression line by hand. A little bit of aid from our calculator. So we have our least squares regression line. We calculated it on the calculator in the last lesson. But today I want to look at what this is actually telling us as far as, how we actually calculate those individual values of slope and y-intercept. But I want to talk before that about this coefficient of determination. This idea of what is how accurate, how strong are the predictions based on this equation that we're using. So coefficient of determination means that it's the percent of variation that in the response variable that can be accounted for by the linear model that relates the response variable to the explanatory variable. Then we know that the other percentage has got to be due to factor something other than the explanatory. So that's a whole lot of words. Sounds really clunky and confusing. Hopefully I'm able to kind of talk you through where it's not as confusing as what it seems. So it's about explaining one variable in terms of the other variable. So it's a change in variability. Well, we know how to calculate percent change. Percent change is just your new value minus your old value divided by your old value. All right, so if you're talking about what was my percent change in my pay, I would take my new pay minus my old pay and divide it by the old pay. So how much did my pay increase? What was my percent change in my taxes from one year to the next? So this is just the basic idea of percent change. Well, what coefficient of determination is doing, it's measuring the percent change of variability. How much did the variability in my guesses change from looking at one variable versus two variables? So let's talk about that variability, that guessing variability. So we care about this response. The number of wins is what we're really interested in this scenario. So let's say I've never even looked at the points per game. I just looked at how many games each team won back in 2011 in the SEC. So in this scenario, if I was going to draw a team at random and I wanted to guess how many games that team won, there's one number that's my best guess to be closer to being right than wrong. And we've talked about that one number best guess in previous lectures. And that's the mean of the distribution. If I ever am just going to get one shot at a distribution, at guessing what I should pick, my one number best guess, it needs to be something towards the center. And we usually, the mean is typically towards the center. If we're done with symmetric distributions, we would pick median in the other case. But mean is the focus for when we're working with bivariate quantitative variables, so two quantitative variables. So if I looked at the mean of each of them, I should have a pretty good guess at how many games this random team from the SEC won. So the mean for this year, I think it came out to be 8.1. So how can we get that? Well, we throw all of our data. We talked about this before, so a data set probably should still be in your calculator. L1, we put our explanatory variables, and then L2, we put our response variables. So I've got my data sitting in L2 on my calculator, and I can just go to one var stats and spit out X bar. In this case, it would be my Y bar, but you get the idea. So one var stats, so we can see that the mean Y bar is 8.1 wins. So graphically, it's going to be somewhere right around there. So that's 8.1 wins. So if I was going to guess how many games that a random team won, this is the number that I'm going to be closer to more than I'm going to be wrong. Now, notice how no teams had 8.1 wins. We did have one team right here that had 8 wins. Auburn did. But then we had about half the teams were above it, about half the teams were below that. So that 8 wins puts us pretty close to the middle. But there's still a lot of variability in that. So I can see that all of these teams missed that guess of 8.1 wins by quite a bit. Right? Some of them had 13 wins. Some of them had 5 wins. All right, so there's a lot of variability. Those blue lines right there, that's the amount of variability that just guessing off of average number of wins introduced. Now, what my least squares regression line should do, when I introduce a second variable, it should decrease my variability. And if we look at it, we talked about the measure variability in the last part, or part 1 on least squares regression, and that was the residuals. How far off are my guesses? So I can see my guess of 8 wins for any random team is really far off. There's a lot of variability there. But when I guess based on knowing points per game, which is what this regression line was, I get a lot smaller variability. So the variability for this team is only that little bit. The variability for this team is only that little bit, and that little bit. And this team was pretty close to being right on, right? This little bit. So what we see is that the amount of variability is decreasing. There's a lot less red on this graph than there is blue. So when I introduce that second variable, I've now decreased the variability of my guess. I've gotten more accurate with my guesses. My data becomes more predictable. That's what coefficient of determination is. Coefficient just measures that amount of variability. How much did our guessing improve when we know a second variable, or a third or a fourth, whatever we want to do? So that's the idea behind how we're going to calculate coefficient of determination. So we're going to take this percent change of variability and just work it out. All right, so percent change of variability. So I'm going to take my new variability, all my red lines right there, 2 variable variability, minus my 1 variable variability. If I only knew the number of wins, or if I knew the average number of wins, all that blue. So I'm really taking that red minus that blue and trying to get that 1 and dividing it by that 1 variable variability. So variability, a lot of times, it'll start to make a little more sense. So I'm going to stop saying variability as soon as I ask, how do we measure it? We talked about that back in previous chapters. What is our measure of variability? How much change there is from one value to the next? Yeah, that's going to be your variance. So variance is our measure of variability. So all these little red lines there, we could work out and try to figure out our variance. Well, we know that variance is nothing more than standard deviation squared. So this is where we build this formula, this concept of trying to figure out the percent change of variability. It's going to take my 2 variable standard deviation, which is just your residual standard deviation. That's what the red represented. That was all of our residuals. How far were we? How far was our observed from our predicted value? So that's going to be measured by the standard deviation of the residuals minus the blue there. So the standard deviation in the number of wins. Standard deviation in the number of wins. I'll write that in blue. So 2 variables is standard deviation of residuals minus 1 variable, standard deviation of just knowing the wins, divided by standard deviation of the number of wins. All that stuff squared out. All right, so before we can do that, this one's easy to do. We know how to find standard deviation of the number of wins. We actually would get standard deviation of the number of wins when we're grabbing this guy right here, the mean for the number of wins. So if I was going to do standard deviation for wins on that same list, we could use either sigma x or sx. Now I'm actually going to use sx in this case, and the reason is because we're building a prediction line. So we're trying to use what we've observed and generalize it to a bigger group or a future group, something like that. So instead of using sigma y, I'm going to use the sy in this case, or the standard deviation of that list. And that comes out to be 3.34. 3.34. So 3.34 is my measure of variability. So what did standard deviation mean? It means on any random guess, I'm typically going to be off by about 3.3 wins. That's all it is. That was your typical deviation from the mean. So if I guess a team randomly, on average, I'm going to miss by 3.3 wins, just by saying 8.1. Okay, just by saying 8.1 on average, I'm going to be off by 3.3 wins. All right, so that's standard deviation of number of wins. What about standard deviation of these residuals? So standard deviation of the residuals is calculated very much the same way. So I'm going to value minus mean over, right? Value minus mean over squared, right? So value minus mean squared, all those added up and divide by however many terms. Now, there's a couple little differences in this case. Here's one. We've already done, residuals already value minus mean, right? Because that's your y minus your y hat, your expected, your observed minus your expected. So we would just calculate all our residuals, square them, add them up, and so on. Now, we also have to change this right here. We're not dividing by n minus 1 anymore. Now we're going to divide by n minus 2. Why would we divide by n minus 2? Well, the reason you divide by n minus 2 is because now we've introduced two variables. So we need two more degrees. We've got to adjust our degrees of freedom because we're introducing another variable. Weakens that estimate a little bit more because now there's a little more play in there, a little more variability in there when we try to get this new variable in. So this is the formula for it. I'm going to show you guys how to do that on the calculator because this list is pretty easy to do because we've already calculated the residual list in the last lesson. So I'll show you how we can get standard deviation of the residuals real quick. So we're going to jump over to the calculator and calculate standard deviation of the residuals for this data set.
So let's look at how we can kind of quickly calculate our standard deviation of residuals using the calculator. So first thing we want to do, remember the formula is the square root of the sum of the squared residuals over n minus 2. Well, n is just your sample size. We got 12 teams here, so n will be 12. We need to get all of the residuals squared and then add them up. I can do that one by one, or we can use the calculator. So we can go to stat edit, get our residuals into L3, which they already are, and then we can go into stat calc and run one var stats on that third list. So when we do this, let's grab the calculator, stat edit, remember, so we've already have our residuals in L3, stat calc, one var stats, and remember I want them to be in L3, so I just need second 3. I'm going to go to calculate. Now what we're looking for is the sum of the squared residuals. Well, if you'll notice this value right here, sum of x squared, well, our x's in this list were the residuals. So this is our sum of squared residuals at 15.2599. So that is what we're looking for in this problem. So we already know n is 12 teams. The sum of squared residuals that we got from one of our stats is 15.2599. Plug them into the formula, and then we get the answer 1.24. So 1.24 is the standard deviation of our residual.
All right, so as we calculated on the calculator, we get a standard deviation of 1.24 because we did our sum of squared residuals and then divided by the n minus 2. Gave us a 1.24. All right, so we can actually key into our little formula right here, standard deviations of residual. Now, what did standard deviations of residual? Remember, this was standard deviation. This is how often a guess was if I'm just looking at number of wins, if I guess that at 8.1. Well, the standard deviation of residuals is the same thing, right? It's how off is a guess, but instead of using number of wins as my guess, I'm going to use my prediction as my guess. So the typical prediction of the response variable, so in this case, typical prediction of number of wins is off by S response unit, is off by 1.24 wins. So that's what standard deviation of residuals tells us, is how accurate are my guesses when I use my prediction line, as opposed to standard deviation of wins. How accurate are my guesses when I use average number of wins to guess? So as we can see, 1.2 wins is how much I'll typically be off if I guess using the prediction line, versus 3.3 wins being off on average when I guess just using the average. So we can already see that we've improved our ability to guess by introducing a second variable. Not just looking at wins, but looking at, or average wins, but looking at points per game as it relates to wins. So this is what we're trying to measure. So that amount of improvement is what our coefficient of determination is. So when I throw all this stuff in the calculator, standard deviation of residuals squared minus the standard deviation of the wins squared divided by standard deviation of the wins. Right? If you guys were to throw that in the calculator right now, I'll give you all a second, y'all can calculate that for me. So put it in the calculator, make sure we are grouping that numerator together. Okay? So throw that in, tell me what we get for the percent change of variability. Okay. All right, hopefully you were able to get it and you got negative 0.862, negative 0.862. And this negative is a good thing in this case. And we saw that because we got more accurate, more precise when we use the prediction line instead of just using the average number of wins. So that negative 0.862, what that's saying is the variability in guessing number of wins decreased, which is good. You want a decrease in variability. Right? The variability in guessing number of wins decreased by 86.2% after we introduced points per game. I guess after we considered points per game. So that tells me points per game is a pretty good predictor variable if I can become 86% more accurate in my predictions, in my guesses of how many wins a team is going to have by using this linear model we've got right here. So that's what this large definition is really trying to say to us. So the way we interpret the percent of variation, so you could say 86.2% of the variation in number of wins in number of wins can be accounted for by the linear model that relates number of wins to points per game. Now the remaining 14% or so the remaining 13.8% of variation has got to be due to factors other than explanatory, or other than the points per game. So that could be things like the weather conditions each game. Maybe if we knew that, we could become more accurate in our predictions. Maybe it was number of injuries per game. Maybe we could get more accurate if we knew that variable in addition. Maybe it was number of points given up per game. Maybe points, number of seniors and experienced or young players. So those are all other pieces of information that would play a role in number of wins that if we knew, we could get more, should become more accurate with our prediction. So that's all that stuff's kind of covered in that 13.8%. So this is how I want you guys to get to interpreting coefficient of determination. Okay? That's how I want to interpret it. Now, there's something really interesting about this 0.862 that I want you guys to look at. Take the square root of that number for me real quick. In your calculator, I want you to do not the negative, because the negative just tells us that we decrease. I just want you to give me the square root of 0.862. So take a second, in your calculator, throw that in, and let me know what you get. I guess tell yourself what you get. You can talk to me if you want to, but I'm not going to hear you right now. All right, so when you keyed that in, you should have got 0.93. Square root of 0.862 is 0.93. Now that number right there should look very familiar to us if you've been kind of following along for the last 3 lectures, so all of our bivariate quantitative data. So we talked about scatter plots, we talked about correlation coefficient also. We had a correlation coefficient. Remember this guy we calculated right up here? Correlation coefficient, the average product of z-scores. When we calculated that, we got 0.94. Well, that's what this number is right here. Now, why is it not the same? Because we have some rounding error and things like that. But this is the idea behind the other way R shows up. So that 0.93 tells me that the square root of my coefficient of determination is nothing more than my correlation coefficient. So when we calculated our least squares regression line, if you guys will remember, when we calculated that least squares regression line, it spit out an A, that gave us a y-intercept, it gave us a B, which was a slope, it gave us an R, which was a correlation coefficient, and it gave us an R squared. So that's what we're talking about as R squared on your calculator. So to calculate correlation coefficient, I kind of go through this process. There's another formula that kind of does this and does it a lot clunkier. Or I can just read off the calculator where it says R squared. So coefficient of determination is nothing more than my linear correlation coefficient squared. And all it's doing is describing for me how accurate my predictions are, how much more accurate my predictions are by using 2 variables instead of 1 variable. All right. Next, I want to look at how we can get these actual values, where the slope and this y-intercept come from. So how we calculate the values in this least squares regression line. So we have least squares regression line here. We will note that LSRL. So sometimes in questions they'll say using the LSRL. That just means using your regression equation. So your line of best fit, your stat calc A plus BX. So the definition of least squares regression line, and it's really just what it says. It's the line that minimizes the sum of the areas of the squared residuals. A sum of the area of the squared residuals. Well, what are squared residuals? That's just a measure of variability. So it's the line that minimizes how much variability there is between what we observed and what we predicted, what we expect to happen. So a couple things that we know are going to happen on this. One, it's going to have the point X bar, Y bar on that curve. Okay, it's got to go through my average X and my average Y. So that's kind of always going to be the starting point on this. So where we had that X bar, that Y bar of 8.1 wins, well, it's also going to give us, work through the point, I think 27.1, if we go and do one of our stats on L2. So if I go one of our stats, on my L1, my explanatory variable, I'm going to get, I think, 27.1 points per game. And we can go ahead and grab their standard deviation also. So standard deviation for that one is 7.16. So 27.1 is about right thereabouts. All right, so had I accurately drawn my graph here, that should be the intersection of my mean wins and my mean number of points per game. So that's the point, X bar, Y bar. So it has to go through that point. And once we know it goes through that point, we then are going to figure out what's the slope of this line so that all of these residuals are minimized. So when they say the sum of the squared residuals, that means when I calculate my residual, I'm going to square it, and it visually makes a square on the graph. And I'm going to square that residual, and square that residual. I'll square that residual and this residual. So I'm just squaring, literally making a square off each residual and when I take all of those squares and add them up, this is the line. This purple line that I've got here is the line that makes all of those areas as small as possible. So if I were to pivot that line down, then all of these squares on top would get a lot bigger, and the ones on the bottom would get a lot smaller. If I were to pivot that thing up, then the squares on top would get smaller, or sorry, in this top corner would get smaller, but down here in the bottom corner, they'd get larger. So this is the balancing point. This line is kind of the balancing point between where all of those squares are as small as they possibly can be. So the line that minimizes the sum of all of those squares. That's the smallest area associated with it. The way that's calculated is using these two little formulas. So first off, you need the slope of that line because we know it's going to go through that point, x bar y. So let's calculate the slope. Because if I've got a point and I've got a slope, then I have an equation for a line, right? Your point slope form, y minus y1 equals m times x minus x1. So if you know a point, you know a slope, you have an equation for a line. So let's start with our calculating that slope. So first things first, your slope is the sy over sx times r. Well, that's your correlation coefficient times your standard deviation of y over your standard deviation of x. Remember, slopes rise over run, but it's the rise variability divided by your run variability. So that's why it's sy over sx. So we're going to take standard deviation, correlation coefficient, 0.94. So this is just measuring all of our variability there, right? And then we're going to multiply that by the standard deviation for number of wins divided by standard deviation for the points per game. And we said that each of those were 3.34 and 7.16. That just comes from one var stats. So we're just going to run one var stats on L1 and L2. When I throw all that in the calculator, I get 0.44. So I get a slope of 0.44. And we talked about in the last lecture, that means for every additional 1 point scored per game, we would expect there to be an additional 0.4 wins on your season total. All right, so now that I have a slope, I can get my equation of my line because I can get my y-intercept. So we're going to take our slope and we're going to match it up with that point that we do know, which is x bar y bar. So it's got to go through the x bar y bar point. So our average number of wins was 8.1 wins minus my slope, 0.44, times my average points per game, 27.1 points per game. We throw all that in the calculator, and we get negative 3.82. Now, if you remember from the last couple lectures, that was negative 3.75 when we did on the calculator. We've done a whole lot of rounding as we go, so that's why we're slightly off here. So now we have our equation of our line because I know my y-intercept and I know my slope. So we get our least squares regression equation, right? The predicted number of wins is equal to negative 3.82 plus 0.44 times the points per game. So this is all the math that the calculator is doing. Am I going to make you guys know or do all of this? No, we've got the calculator. I've told you this 100 times. I don't want y'all doing a bunch of calculations. I want you understanding what they mean. So we're going to let the calculator generate all of that stuff, generate this equation right here. But it's good to understand how it's built because now if we make a change in the graph, if something changes, we can get an idea of how do these values change in response to that. So if I had an extreme value somewhere with a lot of variability, what's going to happen to my slope? What's going to happen? Things like that. So it's good to understand how the equation's built, not so you can build it, but so you can understand how it's impacted if other values come in or if we make changes to our data, stuff like that. All right, so that kind of wraps up everything that I want you guys to know right now for two quantitative variables. We now know how to graph them using a scatter plot. We can describe what that graph means with our shape, our strength, form, direction. We know what outliers look like. We know how to measure that strength, the correlation coefficient. We know how to calculate with the calculator and by hand a prediction line and use that prediction line responsibly, and trying to avoid extrapolation. And we know how to measure how much variability, how much better our ability to guess is using this prediction line, using our R-squared, our coefficient of determination. So that's kind of everything I want to do right now. We'll have little things we add here and there in class, but that's the bulk of it when we're dealing with two quantitative variables, trying to compare two quantitative variables and look for association between them. So that's it, and I will see you in class tomorrow, guys.